Hello and welcome to ChemX. My name is Lucy and today I want to show you how easy it is to train and use your own machine learning models based on your in-house compounds and data. We do this in 5 easy steps right here on the right, and the first is to check your molecules. These are all the molecules that I've uploaded, and you can click on any one of them and you can see the two-dimensional structure as well as the 3D conformation. You can also see all the data that was uploaded along with the molecules and every data point that's been added by ChemX since then. At the bottom there is a warning as well, where you can see there's an undefined chiral center for this molecule, and this just means that the resulting model you would make does not know how to distinguish enantiomers. The second step is to check your target data. In this case, I uploaded a series of PIC50 data. We start off by checking out the histogram. See, this is close to normally distributed, but not entirely. Going down, we see this also in these values, and these warning triangles basically mean that you should probably try a transformation of your data before moving on. If you don't know about this, we will warn you if you try to use such data later on. You will also see your first UMAP. This is what's here on the right, and this is our visual representation of the chemical complexity. The more clusters you see, the higher level of chemical differences in your dataset. Step 3 is to featurize and model your data. You start off by selecting the target data you want. So in this case, I'm choosing the PIC50. This has thrown a warning because it had the non-normally distributed data. I also choose 2 different transformations of this data. You don't need to know specifically how they're done. It's just ways of making this distribution closer to normal distributed. Then you have to select a featurizer. All of these featurizers are different ways of converting molecular structure into vector format that you can train machine learning models from. They have pros and cons, and they are different approaches to the same purpose, but you don't know which one is the right one beforehand, and there's no one size fits all. This is a heat map of the models that were made. So these are the different target values, the original and 2 transformations, and you also see all of the featurizers we have available at the moment. So each cell is the best performing model from a series of attempts on different types of algorithms, different types of hyperparameters, and also the different splits of the dataset into multiple attempts of training the same data to ensure you're not overfitting it. If we have a look at the best model, you can see the confidence intervals for each of these performance measures. So be aware that sometimes the best model is not only 1, it might be 3 that are equivalently good, statistically speaking. And then we have additional metrics down below. You can also have a look how the predicted values compare to the actual values within your test set. The 4th step is explaining your model. There are multiple ways of doing this, but I'll show you a brief example to get you running. In this case, we're only looking at the specific model we saw before that was performing well, and then we look at the 5 best compounds within the dataset. They have these IDs and this performance, and you could find them by clustering, and then you would have, of course, the cluster size. In the UMAP you saw earlier, this is how they look. You can see the yellow dots with the names, that's the ones we're using now. So there's really a cluster here of good compounds. If we have a look at the best compound, you will see the structure, a layman's summary about how it performs and why it's predicted to perform as it is. You can look at different functional groups and see whether or not they help or make no difference in the machine learning model's predictions. So starting to understand which of these functional groups and parts of the chemistry are used by the machine learning model to determine whether or not it's a good inhibitor. For each of these compounds, you see the ID, you see how well it performs. So this value is in this case the PIC50 that they were predicted to have, and you see the Tanimoto similarity below. So in this case, we're looking for molecules that are very structurally similar, but also very functionally different. So the first compound is one of the best inhibitors we found, and all of these compounds are structurally quite similar, but considerably worse inhibitors. When you have a model you like, you simply save it and it's stored over here in My Models, and you can see your own list of models here. When you're ready to screen, you go to Screening Libraries, upload your dataset. This is just a list of smile strings and potentially a name. From here you can go and screen with a model, either one of our many standard models. These are very admit focused at the moment, or you could choose one of your own saved models. When the data is ready, you can simply click and see how the model performed for the entire dataset. If you want to see specifically for each molecule, you can either export data as CSV or use the explanation tools to delve deeper into specific molecules and how these molecules are predicted as they are, why they are predicted as they are. That's all I wanted to show you today, and I hope it has piqued your interest. If it has, be sure to reach out to Raven Biosciences to learn more. And with that, I hope you have a nice day and see you soon. Bye!